Hi, everyone. Welcome to the Physionic podcast. My name is Nicholas Verhoeven. I'm a PhD candidate in molecular medicine and hold my master's in exercise physiology. Today, we're going to be discussing a paper that attempts to look at the effect that alcohol has on muscle protein synthesis, so half of the equation for muscle growth. So we're going to be dissecting some of the data and looking at some of the molecular mechanisms. And then finally, at the end, we're going to discuss really how alcohol specifically affects our muscle growth, which is something that a lot of people are obviously really interested in because they want to build as much muscle as possible, since muscle is such a useful tissue to have. So obviously, especially if you're in your younger years, I know for me, when I was going through my undergraduate degree, I certainly avoided alcohol for quite some time, actually, mainly because I was trying to build as much size as possible. I was religiously going to the gym every other day, and it was relatively nonsensical, to be honest with you. I absolutely destroyed myself for about 2.5 years. But because of that dogmatic understanding of how alcohol might affect my muscle gains, which I thought were just all important, I decided to avoid alcohol. Eventually, I loosened up some, and then as I got more and more educated, then I came to have a lot more flexibility in my life. So I'd like to offer that for you as well, and actually be able to offer you some data to show that could potentially change your perspective on how we're going to look at, or how you're going to look at the consumption of alcohol when it comes to your physique gains or even strength gains. Okay, so a bit on the study design. It's relatively simple. They recruited 8 young people, men specifically, and the study design was what's considered a repeated measure design, meaning that all 8 individuals went through 3 different phases. They went through 3 different conditions. So the 3 conditions were a protein consumption only, so where individuals only consume protein. They did not consume alcohol. Then they had another condition where they consumed carbohydrates and alcohol, so they did not consume any protein immediately after exercise. And then they had the protein and alcohol condition. And what we're most interested in this situation is the comparison between protein and alcohol, as well as protein consumption alone. So how the study worked out was that this was just based off of a single workout, and they kind of wanted to extrapolate from there. They wanted to look at some of the molecular mechanisms specifically, so we're going to be diving into those as well. Not in too extreme of detail, but some level of detail. So they consumed 25 grams of whey protein right after they finished their exercise, and then again 4 hours later. And throughout this period, the researchers were taking blood samples and also taking muscle biopsies, meaning that they were clipping teeny tiny sections of muscle from these individuals so that they can test for these particular molecules that they were interested in. They consumed 6 drinks over a 3-hour period that equated to about 1.5 grams of alcohol per kilogram of weight. So maybe not completely hammered, but close enough. Definitely feeling pretty tipsy, I imagine. And they ended up testing their blood alcohol levels, and they were right around the illegal limit, or at least the current illegal limit of 0.08, maybe slightly below that. So clearly, these people were feeling it, no doubt. I imagine that they didn't need much convincing, or they probably could figure out for themselves if they were in the placebo in the condition that was just consuming protein, or the condition that was consuming protein and alcohol. I imagine they figured that out pretty quickly. All right, and so they also did, the researchers decided to use what's called a phenylalanine trace, which is essentially where they inject an amino acid that has a tag on it, and that tag then gets incorporated into the musculature, and that's called protein synthesis. So then what the researchers can do is they can probe for that tag. Once they take some clips of muscle from those individuals, they can then figure out how much of that tag or how much of that particular amino acid was incorporated into the musculature, which then gives them an indication of the protein synthetic rate, or what's known as fractional protein synthesis. And as I mentioned, they took blood samples to measure their blood alcohol levels as well as their blood sugar levels and things like that. We're not going to be going into any great detail, but of course I'll have the study linked for you so you can check it out for yourself. And then they did biopsies, the muscle biopsies at the 2-hour and 8-hour mark, as well as the rest mark, so before they exercised. Now, in terms of the exercise itself, it was one exercise. They did 8 sets of 5 repetitions at 80% 1 rep max. And the exercise was leg extension. So not a compound exercise, nothing that's going to be too ridiculous, not too tiresome, but doing 8 sets on one exercise, 5 reps at 80% intensity, it's at least stimulates muscle growth. So, we'll see what ends up happening. So to give us a little bit of background so that we're all on the same page in terms of the molecular mechanisms, I'm going to describe this. And if you're listening to the podcast, as always, you can hop on over to the video version and you're going to see these graphics. But again, I'm going to be describing it so you don't feel like you have to follow along and actually watch the video version. So really, basically what we're talking about here is they looked at a variety of different measures. One of the measures was the all-important molecule known as mTOR, and then another one is a downstream molecule of mTOR known as phospho-70 S6 kinase. And so P70 S6 kinase. And then downstream of that, so what that particular S6 kinase does is it activates ribosomes. So what are ribosomes? Ribosomes are the machinery that actually produce the proteins out of our genetic material. So our genes are kept within the nucleus of our cells. So if you take a muscle cell, our muscle cells are one of the unique cells. There are very few cells that have multiple nuclei, so multiple storage sites of genes. And within those storage sites of genes, those nuclei, the nucleus, there are the majority of our genes are kept in that area. So that means that all of the genetic material, all the genetic blueprints for the building of new proteins, of all the proteins within the cell, are kept in this storage place. And what happens is that let's say you want to build protein X. Let's just say there's a protein, it's called protein X. Well, the blueprint is found in the nucleus. So what the cell does is it sends particular factors, what are called transcription factors, particular proteins or molecules that will then go into the nucleus, bind that specific gene that has the information for protein X, and will start undergoing a process called transcription. And then from there, it has created a template of just that gene. And there's a lot of complexity that goes into that I'm not going to go into here. But then that gets exported, that gets moved out of the nucleus, and then that's where the ribosomes come in. So the ribosomes then bind to that gene product, that technically it's mRNA at this point. It goes from DNA, which is the actual gene itself, and it gets transformed into RNA. And then the ribosome clamps onto the RNA, and it starts to spit out it starts to read that transcript. And it produces the protein out of that transcript because it's getting the information just by reading it, just like we read a book. And that new protein is then protein X. So now we've created protein X. And there's a lot of complexity after that, of course, as well, because it needs to go through protein folding and what are called post-translational modifications and things of that nature. But we don't have to worry about that. The point is that ribosomes produce proteins out of this transcript. And that process is called translation. So where P70S6 kinase comes in is that it actually phosphorylates, or it adds a phosphate molecule, or it essentially changes the ribosome in such a way that it encourages the ribosome to produce more proteins. So the big picture takeaway here is what I'm saying is that if mTOR is active, which is the master protein synthesis molecule, then it will activate P70S6 kinase. And once that's active, then it will activate the ribosomes, and that will then encourage the production of protein X. Obviously, there is no protein X. You could replace that with anything. You could replace that with more mTOR protein. You could produce more P70S6 kinase protein. You could produce structural proteins that make up the cell. I mean, any protein that needs to be made will be made through this, at least through the ribosome as its main mechanism. So hopefully that made some sense, and now we can actually start going into the data itself. So based on this data here, they took, again, these measures are based off of a 2-hour time point and an 8-hour time point. And that 2-hour time point, these individuals have already been consuming alcohol, large amounts, I think like 3 or 4 drinks in already at this point. And it's obviously 2 hours after the exercise. Now the rest component, so they've got data there for the rest, and the rest component is obviously for before the exercise and before the consumption of alcohol and before the consumption of either carbohydrates or protein. And what they ended up finding is that mTOR is phosphorylated, which means it's activated above rest in all conditions. So if these individuals exercised and then consumed only carbohydrates and alcohol, still didn't matter. That increased mTOR activity. And remember, mTOR activity is related to greater protein synthesis. So if you have greater protein synthesis, then the idea is that you would potentially have greater muscle growth. But we're gonna put a few caveats on that a little bit later on. So then looking at just straight protein consumption, well, that had a really great effect, and that actually had the greatest effect. So just consuming protein was superior to consuming carbohydrates and alcohol as well as protein and alcohol. So here we're getting a small glimpse that alcohol may have a blunting effect on muscle growth, or at least protein synthesis in this situation. So then they wanted to look at one of the downstream molecules, which I mentioned, P70S6 kinase, and this P70S6 kinase was elevated in 2 of the conditions. So in the 2-hour conditions of protein, so just protein alone, as well as protein plus alcohol. So this then implies that there is a benefit to protein specifically, and alcohol. There is actually a slight reduction in the alcohol condition. So again, we're seeing this furthering of evidence that alcohol negatively affects the effect that you normally would reach with protein. Now, is it severe? No, it's not that severe. It's pretty slight, but still there is a difference between the 2 conditions. Now, they did not see this increased activity with alcohol and carbohydrates, nor did they see this effect when looking at the 8-hour conditions, and that's even with the protein alone condition. So this is all by comparison to rest. So if you're looking at the graphs, you might think, well, maybe alcohol and carbohydrates, which is CHO there, clearly there's a difference, but technically according to statistics, and if I were to go into the statistics more, I would agree that there's no actual difference. So the only difference is with protein, if you consume protein at the 2-hour mark, and even with the consumption of alcohol, there is that slight dampening effect, but you still see a betterment over the resting state. Okay, so that's just looking at 2 pieces of data. They do have more data as well that I'm not going to be presenting, but again, you can check out the paper for yourself. But however, then let's switch gears, and instead of looking at protein synthesis, let's look at protein degradation, so the opposite end, right? So If degradation outpaces protein synthesis, then you have what's called muscle atrophy. So you have the shrinking of the musculature. And if you have protein synthesis that outshines or outpaces protein degradation, then clearly you would have the increase in size of the musculature. So here they're looking at a particular protein that is responsible, or one of the proteins responsible for protein degradation, which is called atrogen. And the thing here is that this particular protein, how it functions is that it tags proteins that need to be degraded, that need to be destroyed. So it adds what's called a ubiquitin tag. And that ubiquitin tag is typically added by what are known as E3 ligases. These E3 ligases are a particular type of protein that atrogen belongs to. And atrogen will just continue to add these tags to these proteins, and then that will signal another bigger complex, a bigger protein known as the proteasome, to come by and essentially gobble it up. So it will destroy it and break it up into its smaller constituent parts. And what they found is actually relatively interesting. So atrogen was reduced at the 8-hour mark in all conditions. So this was not dependent on protein. Most likely it was dependent, and we basically have proof of this because the rest condition wasn't just the fact that we have a difference should be proof enough, that exercise is the reason why you have this decrease in the production of the gene transcript. So again, remember when I said that genes are, let me put this away for a second. When genes are transcribed, so the DNA is transcribed into mRNA or RNA, that is the first step. That doesn't necessarily mean that the RNA will be translated into a protein. But if we make that assumption in this situation, then let's just assume that in this situation that there is a decrease in protein degradation from specifically looking at this one marker, so this atrogen 1 gene being transcribed into RNA. So that gets dampened. So you have less degradation and you have more protein synthesis. A great sign. Now, looking at one more of those markers. So this is the exact same type of protein. So this is an E3 ligase. So again, the same thing. It takes ubiquitin molecules and tags it onto proteins that need to be degraded. And then the protein with all of its tags will get taken up by the proteasome and destroyed. Now, in this situation, they're looking at MRF1. So MRF1 is, yet again, another E3 ligase. And here they're showing, and this is really interesting, that at the 2-hour mark, remember atrogen was decreased at the 8-hour mark only, no differences at the 2-hour mark. But at the 2-hour mark, all three conditions had elevated levels of MRF. So that kind of piques our interest because suddenly we have this increase in protein degradation. So why would we have an increase in protein degradation at the 2-hour mark? Is it because of the alcohol? No, it isn't, because we see that the effects are consistent across all conditions. If you consume protein, doesn't make a difference. If you consume alcohol, doesn't make a difference. If you consume carbohydrates, it does not make a difference. So something is going on here. And here's my speculation. My speculation is that, and I think it's probably right, if I may boldly say so, that you have an increase in degradation because you have more muscle damage. So if you have any sort of muscle damage, the muscle cells can't just have this damage just floating around within themselves. They have to have systems to be able to clean up that stuff and then to go through protein synthesis and replace those damaged molecules, those different proteins. So what they do is they upregulate or start to increase the amount of these ligases and other protein destructive machinery within themselves to clear away all the damaged proteins. So it is part of the recovery process. And that may be why we see then decreases in degradation later on, because we see a quick uptick in the beginning to kind of clean up things. And then once it's been cleaned up, they allow the protein synthetic machinery to come in and to really go off and add more of those proteins that are necessary for the muscle to recover. Okay, and then finally, and if I can go back to this graphic real quick, again, remember that this RNA, once it's been read on protein X, whatever it might be, that gets clamped on by ribosomes, and then they will produce this protein or any number of different proteins. So if we look at that, if we look at what's known as the fractional synthesis rate, so this is an overall understanding or an overall measure of protein synthesis. Remember phenylalanine that I mentioned earlier, that tagged amino acid. If they see greater levels of that incorporation into the muscle cells, then they have some idea at that point then, okay, this has a greater level of protein synthesis. And what they find is that, so we're not looking at the molecules, we're actually looking at the overall process of protein synthesis. What they find is, sure enough, protein alone was superior than alcohol and protein, as well as alcohol and carbohydrates, and of course against rest. So it does show that alcohol blunts the ability for the muscle cells to undergo protein synthesis. Now, can you still build muscle? Yes, you can. It is still elevated, especially if you are consuming protein with the alcohol. However, it is definitely a decrement to your ability to build muscle. Okay, so the conclusions, the takeaways here. Alcohol reduces signaling through this dampened mTOR activity, but not by upregulating disruptive proteins to the process. And I actually didn't discuss those disruptive proteins. There are other proteins that actually inhibit the ability for mTOR to function. We're talking about, or for the ribosomes to function, like there's a protein known as 4-EBP1. That's an example of one of those inhibitory proteins, disruptive proteins. I didn't go over those, but again, you can read about it in the paper if you'd like. Also, different atrophy genes, atrophy being the shrinking of the musculature, MRF, atrogen, those are the two that we looked at, are upregulated and downregulated at the two measured time points. At the 2-hour mark, we saw an upregulation of MRF specifically, and then atrogen was downregulated at the 8-hour mark, with MRF1 likely being present to help with the recovery process, which is what I mentioned earlier, then a reduction in atrogen to facilitate growth. And overall, that means what we saw with protein synthesis is that it has a negative effect. Alcohol has a negative effect on protein synthesis. Now, what's really the takeaway here, though? That you should avoid all alcohol? Be Nick at 18, 19, 21? I mean 21, that's what I mean. I did not underage drink whatsoever. Also being European, there are different laws in Europe. So, but the point is, like, let's say you're younger and you want to go have fun, drink some alcohol, go ham, go absolutely nuts, and maybe it's your birthday and you just want to have a blast. There's no problem with that. Look, go have fun. It's ultimately in the grand scheme of your life, and then even if I shrink that down to the grand scheme of a year or even a month, it's not going to make a difference. However, of course, if this is a continuous thing for you, if you're continuously drinking large amounts of alcohol every single night, or even let's say 2 times a week, large amounts of alcohol, yeah, that can have a negative effect. Not just directly on protein synthesis, but also specifically in the fact that it's going to stop you from being able to work out as intensely the next day. If you need to work out, you can plan around that to a degree, but still you might have some residual effects even a few days later. So that's something to consider as well. So the bottom line is, if you have, let's say, a drink every few nights, that's fine. You're not going to notice a difference. It's perfectly all right. It might affect your sleep a little bit. That's a whole nother discussion. but overall, that's perfectly fine. If you have, let's say, 5 drinks a night, that's going to be a problem. And if you decide to really just go all out, let's say once a month, you're going to be fine. It's not going to have any dramatic effects. You're not suddenly going to lose all your muscle. You're not going to suddenly fall way behind because you indulge once a month, or whatever it might be. So the guidelines are to be, just think about it and decide if you're going to enjoy yourself, and don't worry about the muscle protein synthesis and all that stuff. So there's my points. There's my takeaway. Hopefully this was informative, and hopefully you enjoyed the data as well, kind of going over what this could all mean. And I hope to have the pleasure of speaking with you in the next one. Have a good one, guys. See ya.